In Lecture 3 of this module, we are going to continue to look at the developments in techniques for evaluating P release from soils. And the first thing, or the more important thing now, is we are going to look at P retention and release from biochar. Now, what exactly is biochar? Biochar is created by thermal decomposition of biomass with little or no oxygen. That is either by pyrolysis or gasification. And it is intended as a soil amendment and a means for storing carbon. Very recently, biochar has obtained a lot of interest and people have started using it from the agronomic point of view because biochar acts as a good fertilizer. Now, the history of biochar dates back 2,000 years or so, and it originated in Brazil, in the terra preta soils of Brazil. But what is interesting, it is that it's found only in inhabited areas. So when looking back into details, what we have found is the slash and char procedure, that is, the plant material with the crops remain cut, ignited, and buried to smolder, that means under low oxygen conditions, rather than allowing it to burn, leaves behind a material which is very stable, and that is the idea behind biochar. Now, biochar feedstock, that is the source of material for biochar, can be obtained from several agricultural and forestry byproducts such as wood chips, corn stover, poultry manure, cow manure, or bagasse, that is from the industry, as industrial byproducts may be of sugarcane, which is very common or popular here in Florida. Now, these are just random examples, and all the photographs are taken directly off the internet. And if you go back into the internet, you'll see literally thousands of articles and on biochar feedstock, biochar uses, etc. for agricultural purposes. And currently, we can also get commercially available biochar, and therefore it becomes very important to see what happens when biochar is added to the soil. Now on to some of the biochar research, and I'll be concentrating primarily on phosphorus, which is the topic of this whole series of short presentations. But biochar is known to be very rich, nutrient-rich, not only for major but also for the micronutrients. Now, Spokas and his colleagues looked into more than 4 dozen biochar and black carbon studies dating from 1850 to 2011 to assess the agronomic impact beyond carbon sequestration. But you notice something, that the findings were inconclusive. Half of the studies reported positive effects on yield, 20% no effect, and 30% negative effects. So the overall impact on yield ranged anywhere from plus 200% to negative 87%. See, biochar can have unusually high cation exchange capacity, right? That means it has the ability to hold on and to release phosphorus and other nutrients, but it also appears able to absorb phosphate, which is an anion. And from that article, they say no one knows why. Now, these are some of the things that we need to take care of, and understanding why there are some negative effects and why biochar you can't just apply biochar and feel that everything is going to be okay and that you'll get a high yield and so on and so forth. Now, let us look briefly at soil and biochar properties. Here what we have done is we've taken a look at just 2 soils, a Candler and an Apopka, both of which were minimally impacted. So we looked into water-soluble P, EPC, oxalate P, oxalate iron, and oxalate aluminum, All these parameters have been described earlier, and of course the EPC is obtained from isotherms. Now, so if you look at it, these two different soils have some differences in all these parameters. And interestingly, one thing we need to look at is they have, say, 0.1 EPC for Candler and 0.3 milligrams per liter for the Apopka soil in this particular study. Next, what we are going to look at is the biochar properties. And we looked at two different biochar sources, a hardwood biochar and a poultry litter biochar. Remember, these are what we call as feedstocks, the hardwood and the poultry litter. And they were heated at different temperatures. The pyrolysis temperatures were about 650 to 700 or 700 and 800. And again, look at the EPC. The EPC values are 2.75 for hardwood biochar and 3.60 for the poultry litter biochar. And if you look at the other parameters in the biochar, there is a significant difference, really significant difference between the EPCs of the various biochars compared to the soil, as we just shown. And also, there is a very significant difference in the total P concentration of the hardwood biochar and the poultry litter biochar. These are very, very high numbers. And the corresponding Mehlich-3 values are also very much higher in the poultry litter biochar compared to the hardwood biochar. What this simply means is that the two biochars have different potential to release phosphorus, and at the lower concentration ranges, that is the EPC values, for both the biochars are greater than the unimpacted soils in this study. We move next to see what happens when P is added to biochar. So what we have here is a low P retentive soil. This is actually the Candler previously, as shown in the previous slide. And we looked at soil plus 1% hardwood biochar, soil plus 2% hardwood biochar, and soil plus 5% biochar. So these are batch experiments, very similar to the isotherm experiments we discussed earlier, and various quantities of phosphorus were added, 0, 0.01, 0.1, 0.05, 1, 2, 4, 5, 10, 25, 50, and 100 milligrams per liter. So we did this for both the hardwood biochar, which is on the top, the graph on the top left, and the lower one, the poultry litter biochar. And what do we notice? What we see is, as you add the phosphorus, the release of phosphorus occurs at about the same place, irrespective of the biochar type. Remember, the poultry litter biochar had lots more phosphorus than the hardwood biochar. So what we see here is a property of the soil that determines what happens when biochar is added to it. Next, we look at the biochar additions and P release from a high P retentive soil. This is the Apopka soil, the properties of which you've seen previously. What do you see here? The thing is pretty much similar, but the difference is that you can add more phosphorus before it takes off. So now you see, when it's a low P retentive soil, such as many of our sandy soils, you can add only less phosphorus. And when it's a high P retentive soil, you can add more phosphorus, that is more phosphorus in the biochar before it becomes a problem. Now, biochar can be prepared at various temperatures. And one of the claims that we have is that at the higher temperatures, it will have more, let's say, P absorbing capacity, and therefore should be probably a preferential temperature related or controlled biochar. But we looked at a different sort of biochar under different conditions of temperature preparation. This is in the preparation of the biochar, 350, 500, and 700. And what do we notice? This is the lower graph here. It is the same as the upper graph, which you have seen previously without temperature control in the various biochars. So what do we notice? It doesn't seem to matter what you have in the temperature, the type of biochar that you have. What is more important is the soil, the properties of the soil. Next, we look at the biochar, which was prepared in a Russell kiln with a biochar source from Nevada. And again, what do we notice? These are just 3 reps, and the soil is here in blue. The 3 reps just show nothing has changed at the point till it becomes to be released. Now, what happens after that depends on the biochar properties, how it was prepared, and so on and so forth. Now let us look at biochar additions and P retention. First we looked at the P release pattern. Now let us look at the P retention pattern. This is a simple isotherm type of parameters, but P in solution versus P sorbed in the solid phase. This one is just the soil, the blue line is the soil, and then the other 3 are 3 different rates of hardwood biochar addition, and below it's the same thing, but 3 different rates of poultry litter biochar addition. Now what we see is, as we increase biochar addition, the Smax, or the maximum retention, keeps increasing. And of course, if you look at the difference between the hardwood and the poultry litter biochar, the poultry litter biochar has a higher P sorbed in the solid phase compared to the P sorbed by the hardwood biochar at the same rate of P addition. Now here is what the misnomer comes in. At the lower concentrations, what we have is P release is independent of the biochar sources, but at the same time, the P retention is not independent of the biochar sources, because you see the hardwood biochar is able to have less P in the solid phase compared to the poultry litter biochar. And this is one of the things that people say a biochar is able to sorb P, and earlier we saw nobody knows why, but now we know that it is because it's holding on to the phosphorus. But again, it is not at the low P retention, because you notice that the EPC of the biochar is greater than that of the soil that we studied here, and therefore the biochar was actually a P source and not a P sink. Here it appears that biochar is holding on to the phosphorus. Now, we had looked at the differences in hardwood and poultry litter biochar and how it affected P retention and release. And here are just a couple more of examples, that is of biosolids. The pure maple and pure pine, all of them have very different Mehlich 3 values, as well, whether it is P, calcium, magnesium, and perhaps all the other nutrients as well, and therefore biochar behavior would depend very much on the biochar feedstock for any given soil type. This brings us to the next question, as to what we have when we add biochar as a soil amendment. There are lots of work that's going on which says that biochar holds on to phosphorus. That's absolutely right. We have just seen in the previous slide. So when you add biochar to a soil, this is what happens. This is a soil. The blue line here is a soil. So, and as you add biochar to the soil, in this particular case, we added a 2% biochar, you will notice that the solution P concentration reduces, right? So it actually holds on to the phosphorus. And it is true, there are two examples here. One was the poultry litter, poultry soil, and the other is a dairy soil. But it doesn't matter. Biochar considerably reduces the P, and therefore it is a benefit to the environment. Now, that is exactly what we see now. The question then remains, how stable is this biochar? So we looked at X-ray diffraction patterns of P stability first in the hardwood biochar, and here is a control, that's the lower one, the lower graph here is the X-ray diffraction of the hardwood biochar before the addition of any phosphorus. And the upper graph is the P addition at 1,000 milligrams per kilogram of added P. And what do we notice? There is absolutely no difference. It shows mainly calcite or calcium carbonate peaks and quartz peaks. It does not show a stable crystalline P phase. Now, what does this mean? The phosphorus that is held at the higher P concentrations is not stable and likely to be released with water. But at this point, we need much more confirmation to make sure that this is true by doing a number of desorption experiments. However, there have been desorption experiments by others, and they have actually shown that P is continuously released from the biochar amended soils. That is, it holds on to the phosphorus, but it also releases the phosphorus over time. Now, we have to look at the P stability in the poultry litter biochar. If you recall, the poultry litter biochar had a lot more phosphorus than the hardwood biochar. So we looked at the control, that is the bottom graph here, that is without any phosphorus additions. And that particular graph showed mostly sylvite. Sylvite is potassium chloride salt, which can, of course, be easily dissolved with water. And then we looked at the incubated with phosphorus solution, the same biochar incubated for a while, and then looked at the X-ray diffraction pattern, which is the one on the top, or the upper one. And what do we notice? The sylvite was washed off. Of course, that's the salt, so that's not a problem. And we saw mainly quartz peak, right? And also, interestingly, we have what is known as whitlockite. Whitlockite is a mineral. It's a beta tricalcium phosphate mineral, but it has a slow phosphorus releasing property. All right, so it doesn't mean now there is no strictly stable crystalline P form. We have whitlockite, which is a sparingly soluble form. The question is, remember, we have lots and lots of phosphorus in this particular biochar. So what is going to happen over a period of time? Is this sustainable agricultural practice? Remember, biochar is a very recent development of its use, maybe not more than about 15 years or so since real research was conducted on biochars and its land application for agronomic purposes and so on. Many show very good promise as a nutrient source. And as you've seen earlier, there were some questions why it didn't work in some places, and possibly a part of it, at least, could be based on our understanding of the soils and not so much on the biochar itself. So we come now to a summary of what we have seen and learned so far. Biochar addition effects will differ based on soil type and the P application history. Biochars can constitute a P source when applied to minimally P-impacted sandy soils. Biochar enhanced P sorption at elevated solution concentrations, but that may be reversible, and it's soil rather than biochar properties that dictate environmentally sound P loading rates, that is at the lower concentrations. Thank you.